In the previous lecture, we have studied the Schwarzschild black hole with its two prominent features. First of all, the separation of the spacetime into two causal regions, the exterior and the interior, as well as the geodesic incompleteness in the form of a central singularity. The question is, are these features actually generic for solutions to general relativity? Or perhaps this is just an artifact of a spherical symmetry? I mean, spherical symmetry can indeed be a very strong assumption that changes the qualitative dynamics. If you consider the Newtonian mechanics, as we recall, only the radially falling body would eventually collapse onto the central singularity. And if there is an angular momentum, the body would end on an orbit around it. So, therefore, rotational collapses in Newtonian mechanics have qualitatively different behavior. Maybe something like this could happen in GR as well. Indeed, potentially, there can be a number of possibilities. So, for example, one can think of singularity-free solutions that still have the features of the horizon. On the opposite side, one can think of the solutions that contain the central singularity, but this singularity is not protected by any horizon and is accessible to external observers. So this kind of spacetimes is called naked singularities. And one of the simplest examples is taking the Schwarzschild solution with negative mass. So, of course, another question is the stability of the Schwarzschild solution in the presence of some meta perturbations. Perhaps horizon is not a stable feature, and some time-dependent perturbations of the matter could destroy it. So in the next few lectures, we will show that the black hole horizon, as well as the central singularity, are indeed generic features in general relativity. So that both the naked singularity and the searches for singularity-free solutions with the horizon are not physical. We will do it over the span of the next few lectures, and in this lecture we will start with understanding the framework of the initial value problem. So let us study the meta perturbations on a fixed gravitational background first. So what does it mean for the spacetime to be predictable? So what does it mean for the evolution on the spacetime to be predictable? Well, let's give a few definitions. So, first of all, we want to specify a subset of the spacetime on which we provide initial conditions, and then the evolution of this initial data would cover some subset of the whole spacetime. So we will call such a convenient location of the initial data to be a partial Cauchy surface, and the region of the spacetime where the evolution is entirely predicted by this data to be the domain of dependence of this partial Cauchy surface. So we have partial Cauchy surface sigma is a hypersurface in the full, so hypersurface of the full spacetime, for which no 2 points are connected by a causal curve. So this definition emphasizes the space-like nature of the partial Cauchy surface. Next, it's the domain of dependence. So here we have future and, by the analogy, the past domain of dependence. Which we denote as d plus, which we didn't, d plus and minus, which we denote as d plus or d minus of sigma, is the set through. So this is a set of points in the spacetime such that every future, such that every past or future extendable causal curve will, going through this point, intersects the partial Cauchy surface. So. So the complete domain of the dependence is a union of future and past domains of dependencies. So we have the boundaries of the domain of dependence, which is again the boundaries for the boundaries of the domain for which the evolution is entirely predictable given the data on the Cauchy surface, are called the Cauchy horizons. So we will give a proper definition later in this course, but for now let's state it this way. So boundaries of So, for example, consider the geodesic motion on the space-time. So, given a partial Cauchy surface, the initial data would be the tangent vectors of the geodesics going through every point of this surface sigma. Of course, we can. Of course, the same applies to any matter satisfying some. Of course, the same applies to any matter satisfying the hyperbolic partial differential equations. And by hyperbolic partial differential equations, we mean the equations of the form. We mean second order partial differential equations, which are of the form so where the right-hand side depends on the metric and its derivatives. And the matter fields and their first derivatives. So, let us provide an illustration to our definitions. Let us consider a simple illustration to our definitions. Let us work with two-dimensional Minkowski spacetime, and let the Cauchy surface be the positive side of the x-axis. So we have a two-dimensional Minkowski spacetime. The Cauchy surface is the positive side of the axis, and the domains of the dependence would be given by the line x minus t equals 0 and x plus t equals 0. So this bit would be called the future domain of dependence, and this one is the past domain of the dependence. Again, I want to emphasize that given only partial initial conditions, we can predict the evolution only in a part of the spacetime, in the colored part of the spacetime, while in general the behavior outside of this cone is not predicted. So given a solution, while the solution within this cone is unique, it can be continued in infinite number of ways to the point outside the cone. So to get a good understanding of what I'm saying, let's consider a simple problem. So let us consider the wave equation on the two-dimensional Minkowski. So, exercise. So we have the wave equation on the Minkowski, for which a general solution is known. So we have so we have an advanced and retarded waves. So where f plus and f minus are arbitrary functions of a single argument. Now, let us consider two sets of initial conditions. So that agree on the domain. So the first set of initial conditions is given by f of f at t equals 0 equals to y minus cosine x, and dt of f at t equals 0 equals 0. Let the first set agree with the first one on the positive side of the axis, but is zero on the rest of the axis. So a good exercise would be to build the solutions for both initial problems and then compare their behavior. So this exercise illustrates a simple principle which is true for any problem of this kind, for any hyperbolic partial differential equations. Now, physically, we would like to work with completely deterministic setting, which means that we would like to have a good partial Cauchy surface such that, given the initial conditions, the evolution would span the full space-time. And this is our next definition. So we will call the So we will call the Cauchy surface a partial Cauchy surface whose domain of dependence is the full spacetime. Not every spacetime admits it, so we will call the spacetime to be globally hyperbolic if it admits a Cauchy surface. So a good example of the spacetime that doesn't have a Cauchy surface is again the Minkowski spacetime without the origin. So a good example of the spacetime which is not globally hyperbolic is again a two-dimensional Minkowski spacetime without an origin. So if the origin was cut away from the spacetime, then for any given time slice, we can have curves that end at the origin, and therefore they do not intersect the constant time slice. A good example of a spacetime which is not globally hyperbolic is a two-dimensional Minkowski spacetime whose origin was cut away. So in this case, for any possible partial Cauchy surface, we would have curves, we would have causal curves that end at the origin, and therefore they do not belong to the full space-time. A good example of the space-time which is not globally hyperbolic is a two-dimensional Minkowski space-time without an origin. So in this case, for any partial Cauchy surface, we can have causal curves that either start or end at the origin. And in this case, they will not intersect the partial Cauchy surface, which means that no full Cauchy surface exists. Now, being globally hyperbolic is a very strong property. And in fact, it gives us the intuitive time structure in the full space-time. So the following theorem was proven in Wald. So we have let the space-time be globally hyperbolic. Then, let us have a globally hyperbolic space-time. Then we can infer the structure and the topology of the space-time. So, first of all, there exists a global time function. Secondly, the constant time slices are the Cauchy surfaces, and they have the same topology. And the full topology of the space-time is therefore a direct product of a real line, which is time times the topology of the Cauchy surface. So let us write it rigorously. So we have there exists a global time function such that minus dt is future directed and time-like. And the constant time slices are the Cauchy surfaces. So and the full topology of the space-time is real line times sigma. Okay, so a good example is a Kruskal spacetime. Kruskal spacetime is globally hyperbolic, and the time function is given by u plus v. So, exercise. So, check that u plus v is a time function. And also find the topology of the full spacetime. So, since the u plus v equals 0 is the Einstein-Rosen bridge, with topology with the topology of a real cylinder. So the topology is R times S2. The full topology of the Kruskal spacetime is the full topology of the Kruskal spacetime is R2 times S2. So if the spacetimes are So, if the spacetime is globally hyperbolic, then it is natural to do the 3+1 split, also called the Arnavit-Deser-Misner split, where the 3 corresponds to space-like directions and 1 corresponds to the direction along the global time function. In the next subsection, we will cover the basics, and we will also derive the 3+1 split of the Einstein equations. So let us first see how the geometry works globally for the 3+1 split. So we're given some hypersurface sigma such that for any point P of the spacetime, we can project it uniquely on sigma to get the point with the coordinates xi of the point P. So, in this construction, the spacetime is foliated by the surfaces sigma tau, and therefore, the normal is proportional. The normal is proportional to d tau. So, locally, the metric can be written as ds squared equals minus n squared dt squared plus the three-dimensional part. Where n, hij, and b are functions of both time and space coordinates. So in fact every geometry is locally of this form. However, globally hyperbolic means that geometry is globally of this form, including the special regions. So in fact, any pseudo-Riemannian geometry can be locally put into this form. However, globally hyperbolic spacetimes mean that geometry is globally of this form. So furthermore, note that we still have the coordinate freedom, and we can use it to set the beta, to 0 and n to 1. In this split, n is called the Labs function, and beta is the shift 1 form, shift vector. So know that any geometry can be locally put into this form. However, if the spacetime is globally hyperbolic, it means that the spacetime is globally of this form. So is globally of this form, including the special regions and the asymptotics. Also, know that we still have the local freedom of coordinate reparameterizations. And this freedom can in fact be used to simplify the form of the metric. So, for example, one can locally rearrange the coordinates such that the shift vector vanishes and the lapse equals to 1. We will not use this freedom now. We are not going to use this freedom immediately. So it is also notice that the unit normal is given by n minus n dt. So this is a unit normal, which means that n squared equals minus 1. Checking this remains an exercise. Good. So our next step towards the 3+1 split of the Einstein equations would be to define the curvature on the hypersurface. So from geometry, we have a definition of extrinsic curvature. Where n squared equals to minus plus 1 in the case where sigma is a partial Cauchy surface, or in principle if you take sigma as a time-like surface with the space-like normal. So there's an important property that K is the Lie derivative of the metric on the hypersurface Hij with respect to the normal. So K equals to H. So to the H. Respect to the H. This is a key property which is sometimes taken as the definition of the extrinsic curvature. In particular, both from the definition and from the property, it follows that the extrinsic curvature is a symmetric tensor, as well as it satisfies a number of further properties, including the property on its derivatives. So more details can be found in the geometric literature, and personally I recommend the lecture notes by Gurguillon, which are called 3+1 formalism and numerical relativity. So 3 plus 1 formalism in GR, and numerical relativity. These notes are available online. Good. So our next step is, of course, to define the projection, the orthogonal projector. So So it is defined by two properties. First of all, it is symmetric, and its product on the normal is 0. Secondly, it squares to 1. Using this orthogonal product, we can connect the two connections. So, in these geometric settings, we have two connections. First one I'll call nabla, and this is the connection of the full four-dimensional spacetime. Also, on the hypersurface, we have an induced metric Hij, which defines its own Levi-Civita connection. So, there's a simple proposition, which is also proven in this lecture notes, that these two connections are related by the orthogonal projection. So let nabla connection on and D, capital D, is connection on Hij. So in both cases, we mean Levi-Civita. Levi-Civita. Then the covariant derivatives are related by the orthogonal projection. So I'll schematically write it in this form, whereby the pullback P star, we mean that in indices D rho theta alpha 1 beta 1 equals P rho sigma P alpha 1 mu 1 P beta 1 nu 1 times the covariant derivative. Now, after relating the two connections, we can relate their curvatures. Now, after relating the two connections, we can relate their curvatures. These equations are called Gauss-Codazzi formulas. So consider the projection operators acting on a four-dimensional Riemann tensor. So we have and it would equal to following combination of three-dimensional curvatures. So gamma delta alpha beta plus k gamma alpha k delta beta minus k gamma beta k alpha beta alpha delta. This relation where on the four-dimensional part we have the projection of the four-dimensional Riemann tensor, and on the three-dimensional part, and then on the right-hand side, so these formulas where on the left-hand side we have the projection of the four-dimensional curvature tensor, and on the right side, right-hand side, we have the quantities of the three-dimensional curvature, is called the Gauss formula. Codazzi has derived a formula relating the covariant derivatives of the extrinsic curvature. So we have P gamma rho the proof of this formula can be found elsewhere, including the notes by Kruger-Yohn I mentioned in the previous subsection. So an important consequence comes from contracting the indices of the Gauss formula, for which we find that, in particular, the four-dimensional square curvature plus the four-dimensional Ricci tensor contracted on the normals equals the following combination. Where the raising of the indices is done with respect to Hij. So K and K is the trace. So these formulas historically allowed to write down the 3+1 split of the Einstein equations. So the Einstein equations where for simplicity we will use the local coordinate freedom to set n equals 1, b equals 0 locally, can be written as follows. So the four-dimensional Einstein equations are given by this, where the stress tensor is in its turn given by so rho for density and mu plus the pressure plus the remaining part. So such that p times n equals 0 and s times n equals 0 allows us to write the following decomposition of the 3+1 equations. So we're given two dynamical equations. First of all, dt of hij equals to minus 2kij, and where dt of kij is given by the three-dimensional Ricci tensor plus combinations of extrinsic curvature plus terms coming from the stress tensor. Plus two constraints. So these constraints are related to the Bianchi identities for the four-dimensional Ricci tensor. So the first constraint is scalar, and it reads as where we easily recognize the right-hand side of the contracted Gauss formula. And it equals to 16 p times the density. And we have the second constraint, which is a vector constraint. And it's given by ji minus dik equals 8 p times the pressure. So here we recognize the right-hand side of the Codazzi formula. So this is called the Hamiltonian constraint. And these are the momentum constraints. Let us a bit motivate the namings. So the first two equations are clearly the hyperbolic equations, because taking the time derivative from the first line and substituting the second line, we're getting some kind of a hyperbolic equation for the metric on the hypersurface. The next two equations are not dynamical. There are no time derivatives. And therefore we can interpret them as constraints. Now, these constraints can be interpreted in two ways. First of all, these constraints can be linked to the, as I said, to the Bianchi identities from the four-dimensional Ricci tensor, which now were decomposed into 3+1 split through the orthogonal projection. So in particular, it shows that in general, within the system of Einstein equations, in 4 dimensions there are only two physical degrees of freedom. So indeed, if we have, so indeed, since the Einstein tensor is symmetric, and it has 10 components, so indeed, since the Einstein tensor is symmetric and it has 10 components, we have 10 equations. However, four of these equations are pure gauge because we have the reparameterization freedom in 4 coordinates. So therefore, we have 6 independent equations. However, we also have, as we have just shown, 4 constraints. So therefore, in 4 dimensions, we have only 2 independent degrees of freedom. So -4 So the Einstein theory has only 2 dynamic degrees of freedom, and therefore, for example, the graviton has only 2 polarizations. Secondly, we can interpret this constraint in terms of the initial value problem. So, given that the evolution equation is given by the first system, the second system actually constrains the initial data. So we cannot supply the first system with arbitrary data. The initial data must satisfy the Hamiltonian and the momentum constraints. To summarize the previous subsection, the initial value problem is given by the hyperbolic equation and the boundary data, where h and k on the partial Cauchy surface must satisfy further constraints, the Hamiltonian and the momentum constraints. So, naturally, the question is if the evolution of this data is unique, and if not, under which circumstances. So naturally, the next question is if the evolution of this data is unique, and if it is unique, can we say some global properties about the spacetime? So the following result is of fundamental significance in general relativity. So we have a theorem by Scheke-Brouillard and by Gerach. So by Scheke-Brouillard and Gerach. So 1969. So let us have the initial data set, which is good in a sense that it satisfies the vacuum Hamiltonian momentum constraints. Let us have the good initial data on a partial Cauchy surface. Good in the sense that it satisfies the constraints. Then first of all, there's a unique evolution of course, up to a diffeomorphism of this spacetime, which we'll call the maximal Cauchy development. So then a unique spacetime which is called maximal Cauchy development, and this spacetime, first of all, and this spacetime is the result of the evolution of the initial data, in the sense that, first of all, it satisfies vacuum Einstein equations. Secondly, it is globally hyperbolic, with sigma being its Cauchy surface. Then H and K are indeed the induced metric and extrinsic curvature on sigma. And finally, any other spacetime satisfying these constraints is isomorphic to a subset of the maximal Cauchy development. So we have, first of all, J mu satisfies Einstein. 2 is globally hyperbolic. Sigma is Cauchy surface. Then H and K induced metric and extrinsic curvature. On sigma. And finally, any spacetime satisfying 1 to 3 is isomorphic to subset. So which means that we cannot have a more complete evolution of this initial data, in the sense that this Cauchy development is maximal. So while this theorem was stated for the vacuum Einstein constraints, in fact it works for any good matter. Good in the sense that its equations of motion satisfy, well, are of the hyperbolic form. So have vacuum. So for any hyperbolic matter. So it can happen that the maximal Cauchy development is extendable. So it is a subset of some larger spacetime. Then by this theorem, we cannot predict what happens in the external regions. So in the subset times the in the exterior subset larger space-time. This, of course, is this, of course, raises the question. Of the predictability in GR, because, of course, we're doing classical physics, and we would like to have our physics deterministic. So we would like to have that given some initial data, preferably as complete as possible, we would have an evolution that would cover the full behavior of the bodies we are studying. So this theorem alone leaves this possibility open. Now, let us study some examples. The first example will be the example where the partial Cauchy surface is incomplete, and therefore we cannot predict evolution in the full space-time. So let us consider the three-dimensional hypersurface given in Minkowski coordinates by x, y, z such that x is greater than 0, and hij is simply the Euclidean metric delta ij, and the extrinsic curvature is 0. So, of course, the maximal Cauchy development of this data would be the light cone. So would be the exterior of the light cone. Namely, namely, the region inside the wedge will be the maximal Cauchy development and not the full space-time. So our next example is more interesting. Good. So in the previous example, the maximal development was extendable, but it was also due to the extendability of the initial data. So is actually assuming the inextendability of initial data sufficient? No, we're giving a better example. So let us consider the Schwarzschild with a negative mass. So the metric is given by ds squared minus 1 plus 2 module over r dt squared So as you can notice, the horizon feature is absent because the metric is everywhere non-degenerate, except for the central singularity. The central singularity is still there. It's still present for r equals 0. And it is an essential singularity. The curvature scalars diverge. So, in other words, this is a naked or unprotected singularity. Now, as an initial data, let us take the constant time slice For example, the time slice at time equals 0. So we have sigma h k initial data and sigma corresponds to constant time slice. It's actually a good exercise to check that the extrinsic curvature for this data is 0. So, of course, the initial data is inextendable. However, it is not geodesically complete because we have an eighth singularity. And this feature turns out to be pathologic. Because, so if the spacetime is not geodesically complete, it means some part of the evolution of the geodesics is effectively hidden by the pathologies of the spacetime. So, in particular, as we now show, we may have geodesics reappearing from the next singularity at later times, which of course does a huge blow to the predictability. So, consider the outgoing radial null geodesics. So, as you recall from the previous lectures, they are given by dt over dr equals 1, so in this case plus 2m minus 1, which is roughly r over 2m for small m. For small radius. So, at the singularity, so around the naked singularity, we basically have that the evolution is given by so, in particular, the time, which is again an exterior time coordinate, the time coordinate with respect, the time coordinate of the asymptotic observer. And so for the outgoing geodesics, this time coordinate is finite. So in these words, we indeed have null geodesics, and in fact we'll have all kinds of geodesics emerging from the naked singularity. That are capable of reaching the infinity. So, the domain of dependence of this data would therefore look like, so this is sigma itself, and then we have the future domain of dependence, and similarly we have the past domain of dependence. Of course, this is not the whole space-time, and so just to recollect and emphasize it again, the data, so the initial data would predict the space-time, the geometry of the space-time, only in the given domain. So we know that the geometry is that of the naked singularity only within the colored regions. outside the colored regions, there are infinite possibilities. And we can continue the data from the colored regions to the uncolored regions in infinite number of ways. And stating that the geometry is everywhere governed by this metric is just one of the multiple variants. So, to summarize, the geodesic incompleteness of the initial data means that this initial data is bad. Okay, so is demanding the geodesic completeness and inextendability of the initial data sufficient? No. Let us consider the final example. So let's take as the initial data. So let's have the initial data defined on a hyperboloid within the past light cone in Minkowski spacetime. So sigma is minus time squared plus x squared y squared z squared equals to -1. And we have time less than 0. So in Minkowski. So clearly the maximal development is basically the interior of the past light cone. So we have that sigma is given by So sigma is this hyperboloid, and there clearly exist inextendable null curves that do not intersect sigma. These are the null curves that belong to the boundary of the light cone. So the maximal development is the interior of the light cone, which is extendable in the sense that we can add the boundary. So here the reason for the extendability of the maximal development is the fact that the initial data surface is asymptotically null. So at large distances, the asymptotics of the surface is that similar to null hypersurfaces. And in other words, this allows the transition of the information from the infinity. Good. So to summarize the previous section, we want our initial data to be good in the global sense. So it must be inextendable, it must be geodesically complete, and there should be nothing coming in from the asymptotic region. So presumably we have cared for all possible global properties of the initial data, and therefore we can expect that the maximal development will be predictable. First of all, let us summarize in a definition what we mean by the good initial data set. So So we will call the initial data sigma, metric, and extrinsic curvature as the asymptotically flat end if it satisfies the following properties. So first of all, sigma is diffeomorphic to the three-dimensional. So first of all, yes, sigma is diffeomorphic to three-dimensional Euclidean spacetime, maybe except for some central ball. So sigma is homeomorphic to R3 without potentially a ball. So some closed ball centered at the origin. Secondly, we want the initial data, that is the metric and the extrinsic curvature, to have properties similar to the Minkowski spacetime at the asymptotics. So we can formulate it as follows. So the pullback of the Euclidean coordinates to define the xi chart on sigma, and in this chart we have hij behaving as the Euclidean metric plus some high order corrections. So R equals and this happens as R goes to infinity. And the third one would be to constrain the derivatives. So we have hij k equals O of 1r squared and kij k, the comma stands for partial derivatives, is O of r cubed. Good. So an initial data set is called asymptotically flat with n ends if it's the union. If it's a union of a compact set with n asymptotically flat ends. So Good. So what about known spacetimes? Well, if you take the Schwarzschild solution in the Schwarzschild chart, so we have sigma given by times in equals constant and radius greater than 2m. So in this case, this is asymptotically flat data with one end. For the Kruskal, the initial data is given on the u plus v equals constant, which, as we remember from the Kruskal diagram, covers two disconnected regions, which are asymptotically flat. So in other words, and this of course was also seen from the Einstein-Rosen bridge. So the Kruskal initial data is asymptotically flat with two ends. Now that we have defined what we mean by the good initial data, that is asymptotically flat and geodesically complete, it is reasonable to expect that the maximal development of this data is inextendable. Indeed, if it's not, we are in a big trouble. I mean, we have provided a good initial data, and the maximal development, the evolution of this data, does not cover the full spacetime. It means that general relativity is therefore has big pathologies with predictability, which casts doubt on the full theory in a classical sense. In a classical sense, the theory which is not deterministic is in fact pathological. So, therefore, Penrose has formulated what is now called the strong cosmic censorship conjecture. And it states that if we have the good initial data, the maximal development is inextendable. So, let us write it a bit more rigorously. So, let sigma h and k be geodesically complete asymptotically flat data with n ends. And this data is for the vacuum Einstein equations. Then, generically, the maximal Cauchy development is inextendable. One of the key words here is generically, as we'll show in the following examples and counterexamples. So, what's the current status of this conjecture? Well, it is proven to be correct for a number of important cases. So, first of all, let us consider the initial data which is close to Minkowski. So, So it was only in early 1990s that Christodoulou and Kleinemann, actually 1994, that they have proven the full non-linear stability of the Minkowski spacetime with respect to matter perturbations. So, in other words, if the perturbations are sufficiently small, within some finite neighborhood of the Minkowski spacetime, the spacetime would still settle down to Minkowski. So this was proven by Christodoulou and Kleinemann in 1994. Then, very recently, in fact 3 years ago, the result was extended to the Schwarzschild spacetime. So, think about it. The Schwarzschild solution was discovered in 1916, and it took more than 100 years to show that this solution is in fact physical in the sense that it is stable to perturbations, stable in a full nonlinear regime. So there was a big collective of authors. So Michalis Dafermos, Gustav Holtzegel, Igor Rodnyansky, and Marika Taylor. So it was done only recently in 2021. Now, the next step is of course the Kerr spacetime, but we don't have any results so far. It is still work in progress. And so this is still work in progress, done by this group. And the reason why it is a work in progress is because of the following features of rotating and charged black holes as well. So now, why we have the word generic? So the reason is that as we will see in the future lectures, the charged black holes, that is the Rice-Nordstrom solution, and the rotating, the Kerr solution, they in fact have a Cauchy horizon. But the Cauchy horizon, the second horizon, is hidden behind the first horizon. So, in other words, there exists a Cauchy horizon, but it is hidden from us. In the whole exterior. So, as we will see in future lectures, the charged black hole, that is the Rice-Nordstrom, and the rotating black holes, that is the Kerr black hole, they have two horizons, and the interior horizon is actually the Cauchy horizon. So it is the boundary of the deterministic development of the exterior data. However, in both of these solutions, this feature, which breaks the predictability, is hidden in the interior of the black hole, and therefore it is a mild pathology. However, the existence of this Cauchy horizon leads to the phenomenon called Cauchy instability. That is, if we send two signals at different times, at different times into the black hole, then they will arrive to the Cauchy horizon at the same value of their finite parameter. So what is generic? So as we'll see in the future lectures, in the charged black hole, that is Reisner-Nernstrom spacetime, and rotating black holes, that is Kerr spacetime, they feature two horizons. And the interior horizon is actually the Cauchy horizon for the initial data. However, this is a mild pathology because this feature is hidden in the interior of the black hole. This feature, however, leads to Cauchy instability, so the interior horizons are believed to be non-stable. With respect to any possible perturbations. However, there is so far no good resolution of this problem, and therefore both charged black holes and rotating black holes are an interesting laboratory for the quantum information thought experiments. So, to summarize, generic is Reisner-Nernstrom, Kerr, feature Cauchy horizon in the interior. So, to summarize, it is still believed that a generic initial data set sufficiently close to Reisner-Nernstrom and Kerr would still produce an inextendable maximal development. So, as a conclusion, the conjecture is naturally extended to include matter with hyperbolic equations of motion. In fact, when considering matter in future sections, we would prefer to consider physical matters, as we'll explain in future lecture. So we would prefer to have positive energy density and no superluminal propagation. So to summarize, it is still believed that taking the initial data sufficiently close to Reisner-Nernstrom and Kerr will produce an inextendable maximal Cauchy development. So, as a conclusion, there are 2 points. First of all, this conjecture is naturally extended to include matter with hyperbolic equations of motion. Secondly, as we have just said, proving the strong cosmic censorship conjecture and the related weak cosmic censorship conjecture are still a work in progress, even when the initial data is sufficiently close to well-known solutions. So therefore, it is still one of the main driving goals of the mathematical general relativity.